Welcome to the second lecture of the numerical linear algebra and application. Let us recall quickly what we did in the last lecture. We started with the solution to the linear systems Ax is equal to b. Then we also did it, what are the difficulties arising in trying to find out the solution to the linear systems. We also did it eigenvalue problems. We also did singular value decomposition and so on and so forth. Well, having had this background, today we will be using some examples and some theoretical issues and finite digit arithmetic and so on and so forth. Suppose we want to compute En. Let's say En is equal to integral 0 to 1 x power n e power x minus 1 dx, always positive in the interval 0, 1 for various values of n. N could be 1, n could be 2, n could be 3 and so on and so forth. So therefore, En is equal to, here you see here, En is equal to x power n integral 0 to 1 e power x minus 1 dx minus integral 0 to 1 d by dx x power n integral e power x minus 1 dx. So essentially what we are doing in this is, you have two functions x power n e power x minus 1. So first function into integral of second function minus d by dx of first function into integral of second function all dx, right? This is what the rule we use it. So when you simplify this integral, it turns out to be x power n times of e power x minus 1 and upper limit and lower limit 0 to 1 and minus of integral of 0 to 1 nx power n minus 1 e power x minus 1 dx. Further, if you simplify, this turns out to be 1 power n e power 0, and anyway this is 0, and this is x power n minus 1 e power x minus 1 dx. So altogether it turns out to be 1 minus n times of e of n minus 1. So therefore, what you can see from here is, when you are trying to evaluate this integral, En is equal to integral 0 to 1 x power n e power x minus 1, by integration by parts in the given interval 0, 1, it turns out to be 1 minus n e power n minus 1, where En is integral 0 to 1 x power n e power x minus 1. So if you look at into the recursiveness, therefore the recursive formula is En is equal to 1 minus n of En minus 1, n is equal to 1, 2, 3, etc. This is what is called recursive formula. So now you will be very clearly knowing what is the recursive formula, what is the iteration formula. What are the instances we use recursive formula, what are the instances we use iteration formula in order to find out a best approximations. Now, as a matter of curiosity, if you put n is equal to 0, E1 is equal to 1 minus 1 into E0. What is E0? E0 is simply integral 0 to 1 e power x minus 1 dx, which simply turns out to be 1 minus 1 by e. So therefore, this ultimately implies E1 is equal to 1 by e, that is 0.367879. So that means 6 digits, 6 digit arithmetic, 6 digit arithmetic. So that means we are interested in the 6 digit arithmetic. So assuming that this will give you a best approximation. So therefore, you should be very clear when you are doing the numerical computation. You could be doing what we call the chopping, or you could be doing the rounding of the numbers depending on the what accuracy you require. 2 digit arithmetic, 3 digit arithmetic, 4 digit arithmetic, 5 digit arithmetic. So accordingly, we do the finite digit arithmetic approximation. But if nothing is mentioned in a particular instance, you always try to do 4-digit arithmetic at least. That will give you a better approximation. Now look at this as a matter of curiosity. If I do put up the n is equal to 2, you see here what happens? For n is equal to 2 case, E of 2 is equal to 0.264242. You see here, and E of G is minus of 0.68480. This is the numerical computation. When you rearrange these terms, that means 1 minus E of n upon n. So if you rearrange like this, and which is essentially En minus 1, right? For n is equal to backward. So this n minus 1, n minus 2, like that, 4, 3, 2, 1. So therefore, what is the observation we can see from here is En is equal to integral 0 to 1 x raised to the power n e power n minus 1 dx. This is essentially less than or equal to integral 0 to 1 x power n dx 1 by n plus 1. Okay, like that one can do for n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, and so on and so forth. You can do that. So therefore, ultimately, let's say that when n is equal to 20, what would happen? So when n is equal to 20, E of 20 is less than or equal to 1 by 21. Say E20 is 0. That means 0 is less than 1 over 21, right? So 0 is less than or equal to 1 over 21. So that means the 1 over 21 is always greater than or equal to the 0. That means this is a correct, right? So the essentially what we do is, when you try to see that the values are actually the finite digit arithmetic, it is helping a lot. So therefore here 1 by 21 is greater than or equal to 0, which is correct. So that's how you do the computation for using the finite digit arithmetic. Now let us go to the very basic fundamentals of the finite digit arithmetic. You see, every number can be written as x is equal to plus or minus r times of beta power e. You see here this one. So what is e? E is the exponent and r is the significant and beta is base of the number system. So let mu is the machine precision. Let mu is the machine precision and floating point of x plus y. So we write it as FL of x y, that is equal to x y 1 plus delta, where dot is any basic operator. So it could be multiplication, it could be addition, or it could be direct sum or something like that. So we can have the different notations lead to the different formulas. So therefore, whatever we use it, we write this as the exponent, significant, and b is the base of the arithmetic. So the formula is floating point of x plus y is nothing but x y 1 plus delta, where this is the binary operation, any of the basic operators. And delta is less than or equal to mu. Delta is mod of delta is less than or equal to mu. So this can be written as 1 by 2 times of beta power 1 minus t if you are using the rounding, and this is beta raised to power 1 minus t if you are using the chopping. This is a very basic concept which we do use in the numerical calculations. Let us see the floating point. So x is equal to plus or minus r times of beta power e, right? Where e is the exponent and r is the significant and beta is the base of the number system. So let us see mu is the machine precision. So if you apply this machine precision, you can write it as floating point of x y is nothing but x plus y times of 1 plus delta, where delta is any of the four basic operators. So we can write this as delta is less than or equal to mu, that is 1 by 2 times of beta raised to the power 1 minus t, beta raised to the power 1 minus t if you do the chopping. Well, look at this. Look at this example. by what we can compute is recursive computations are those which are performed recursively so that the computations of one step depends upon the results of the previous steps. Those is what is called recursive computations. So one should be very clear about the recursive computations and iteration computations. And you also have to be very clear what are the instances you do use relative computations, what are the instances we use the iterative computations. So the errors in the computations are measured either by absolute error or relative error. See that in many instances we are very clear that we do find out and we do compute the errors arising due to absolute error or relative error. But remember that we will be doing some example, relative error makes more sense than the absolute error. That means you want to find out the relative error and show that relative error happens to be a better measure than the absolute error. Now let us look at into this example. So also you see the relative error gives an indication of the number of significant digits in an approximate answer, right? Whereas the relative error in representing a real number x by its floating point representation FL of x is bounded by a number mu called the machine precision. So that means whenever you are trying to do the relative error, you should be careful about the floating points, how you do compute the floating point representation. So for this we have a what we call round of errors due to cancellation and recursive computations. Subtractive cancellations or catastrophic cancellations are a phenomenon in which a number of significant digits in a computations gets cancelled due to subtraction of two almost equal numbers. So when you have a two almost equal numbers, then you do have a catastrophic cancellation. It is very, very important. So that is catastrophic cancellations. Well, now let us look at into few examples in this direction. Suppose x is equal to 5 by 7, y is equal to 1 over 3. Now I want to use 5-digit chopping, calculate the approximate value, absolute value and relative value of x plus y, x minus y, x multiplied y and x by y. So therefore you can see that x is equal to 5 by 7. So I do write it as 0.714285. That means 7 7 ja 49, 10 will remain, 7 1 ja 7, 3 will remain, 7 4 ja 28, 20 will remain, 7 2 ja 14. So therefore 7 8 ja 56. So like that you can write it as this number. Similarly 1 by 3. So you know very well this is, you can write it as 3 3 3 3 etc. Now let me compute floating point of these two numbers and similarly floating point of this. So now add up all these things. So ultimately we will end up with 0.10476 multiplied with 10 power 1. So this is the one which you get it. Okay. So the idea is when you are using this finite digit arithmetic, you should be careful about how actually these values will be coming up through the process called rounding. Now let us look at into this example. What is the true value is x plus y. Simply I do compute 5 by 7 plus 1 over 3. So it is 21, 15, 7. So it is, so it turns out to be something like 22 upon 21. This is the number which I am getting, right? But when you write this absolute error, so when you write this absolute error over here, you see here true value minus floating point of n. So it is the 22 by 21 minus 0.10476 times of 10 power 1. So this you need to compute it. So when you compute this, what you get is at the end you do get as the absolute error is 0.190 10 power 4 and relative error turns out to be the 0.18 to 10 power minus 4. Now you see out of these things, so relative error turns out to be, this is 0.182 and absolute error turns out to be 0.190. 0.190. So therefore there is a huge difference between relative error and absolute error. Well, we can also do some computations by using these operations. You see the operations x plus y, direct sum. So this is the result which you are getting. This is the result which you are getting, x minus y. This is the result which you are getting, and x multiplied with y. This is the result which you are getting, x by y. This is the result which you are getting. So this is the actual value, and this is the absolute error, and this is the relative error, and these are the operations which we get over here. Now, if you look at very clearly how you are getting these operations, so absolute error and relative error, see that relative error in all the cases is much smaller than compared to the absolute error. So therefore, there is a need to look into these issues very carefully. So that is the reason that in almost all the scientific computations, we try to do the what we call the relative error rather than absolute error. So now we are ready to define formally. An algorithm is an ordered set of operations, logical and arithmetic, which when applied to a computational point defined by a set of data called the input data, produces a solution to the problem. A solution comprises a set of data called the input data. So that's how we do define what we call the algorithm of a particular example. Now, let us see the solution of an upper triangular matrix. You know, all of you know very well upper triangular matrix. So that is upper triangular matrix. You do find out examples in the image processing, tomography, and many more applications. Let us consider the system Ty is equal to B, where T is equal to T is nothing but Tij. T is the Tij. So non-singular upper triangular matrix. Then we write it as T11 Y1, T12 Y2, T1n Yn, etc. So you do get as all the B1s are this side. So you do have this matrix, and this is all zeros, and these are all non-zeros. You do have it. That is the specialty of this matrix. So this is what is called the upper triangular matrix. How you find out the solution to these upper triangular matrices. Now look at this. The algorithm will be as follows. So you have an input, you have an output. Input is an n by n triangular matrix T, and output is the vector y is equal to y1, y2, yn. And step 1 is we try to compute this bn by tnn, and then you go to this algorithm. You could able to find out the solution to this algorithm. This is what is called back substitution using upper triangular matrix. We also do have forward elimination for lower triangular matrix. So lower triangular matrix means you do have this diagonal, all are zeros, so you do have a non-zero elements. That is what is called lower triangular matrix. So you do find out applications in many engineering. So this will be also as follows. So you do have L is equal to Li, B is equal to Bi. Input is n by n lower triangular matrix, and L is the vector, and output vector is I want to find out y1, y2, yn such that L of y is equal to B. And step 1 is y1 you compute it, and step 2 is compute like this. So we should be able to get the solution whatever is we desired. Now let's see that backward error. So we call it the backward error is always mod of y minus x, where x is unknown, x is unknown and y is unknown. So mod of y minus x is called backward error. Relates the error to the data of the problem rather than the problem solution. So backward error means always it is y minus x, right? Relates to the error to the data of the problem rather than the problem solution. And what is the forward error? Forward error is mod of fx, that is mod of fx, that is function value evaluated point, and it is f prime of x approximation. So there is called forward error and backward error. Backward error is related to the data y minus x, whereas forward error related to the solution to the problem. So that is the, therefore forward error will have a more meaningful than the backward error. But if one wants to have the complete error, so you should compute backward error as well as the forward error. Now let us say, suppose we would like to estimate the value of x is equal to e power x at x is equal to 1. So if you write f prime of x, it is 1 plus x square by 2, x cube by 3. So we truncated. So what is, so that means fx is known at x is equal to 1, f prime of f cap of x is written. What is f of 1? F of 1 we know it is 2.7183 and f of cap 1 is 2.833. So forward is nothing but fx minus f prime of x, we can find out. And the backward error is nothing but find the backward error is nothing but it is simply it is nothing but y minus x. So at x is equal to 1, what is y? You can compute it, that will give you the backward error. Now if for e power x, y is equal to log of fx and y is equal to log of f cap of 1, so which you can write it as after simplification 1.0414. Because the backward error y minus x turns out to be, so you see that 0.0414. Okay, so what is the forward error? Forward error is 0.115. So 0.115 and 0.0414. Backward error is very less. So forward error is 0.115. But backward is 0.0414. Less forward error preferred. So therefore, since the error is becoming very small, so we prefer the backward error. So the error not from the solution, error from the data of the points. Well, so similarly we do have a backward and forward stability. An algorithm is called backward stable if for any x it produces a value f cap of x with a small backward error. So if the backward error is very small, we write it as a backward stable, and that is f cap of x is equal to f cap of f of y for some y close to x. Similarly, forward stable can be defined as an algorithm is called stable if it is backward stable. So that means, so an algorithm, similarly you can write it as a forward stable can be defined. An algorithm is called stable if it is backward stable, right? Okay. Well, so we should not form the opinion that if a stable algorithm is used to solve a problem, then the computed solution will be accurate. Okay, we should not get into such problem. A property of the problem is called conditioning, that will give you the accuracy and inaccuracy of the computed results. This is quite often we use it. The what is called conditioning. So the conditioning of a problem is concerned with how the solution of the problem will change if the input data contains some impurities. So if you have impurities, how it contains, it will be computed through the conditioning. This may be due to round of errors and a discretization of the errors. So discretization is very important while trying to find out the numerical solutions to the differential equations. Now let us look into the perturbation analysis. A theoretical study done by numerical analysts to investigate these effects. How actually these changes are taking place, errors, which is independent of the particular algorithm used to solve the problem. This is what is called the perturbation algorithm. And all of you knowing very well, quite often we do come across ill-conditioned system, well-conditioned systems. So essentially, what is ill-conditioned system? Ill-conditioned system is if a small relative perturbation of data can cause a large relative errors in the computed solution, then it is called ill-conditioned system. Ill-conditioned systems also we call it as a badly conditioned systems. Otherwise, the system is said to be well-conditioned. So if the problem is well-conditioned, there is not much to do it. But unfortunate thing is, in many of the realistic applications, the system turns out to be, the physics of the problem demands us to write a system which turns out to be a ill-conditioned system. So therefore, there is a need to find out a solution to these ill-conditioned systems. So let us say x is the original data, fx is the solution. So y is the slightly perturbed data, fy is its solution. Then the condition number of problem f with respect to data is written as relative error in the solution, nothing but relative perturbation is nothing but yx minus y. So a problem in terms of condition number, when you calculate the condition number, if the condition number is bigger and bigger, then the system is said to be ill-conditioned. And if the condition number is very small, let's say 1 or 2 or 10, 15 like that, then we call it as a well-conditioned system. And similarly, condition number of a, not only for the things, condition number of a function of one variable also we can have it. So if fx is a differentiable function of one variable, so if it is a single variable, then it is easy to see that for small perturbation, the condition number is denoted by, we call it as a cx. So you can find out mod of x, we can find out mod of f prime of x, and you can find out f of x. So we should be able to compute what we call the condition number, and if the condition number is small value, let's say 1, 2, 3, 4, 5, 15 like that, then it is a well-conditioned system. If it is a bigger number such as 10 power 4, 10 power 5, then the system will become a ill-conditioned system. So essentially, small condition number will lead to a well-conditioned, and a bigger condition number will lead to a ill-conditioned system. So for functions, let fx is equal to e power x. So f prime of x is e power x. Therefore, I can write it as cx is equal to mod x into e power x upon x. So x, which is large for large values of x. That means a small relative error in x can produce a large relative errors in e power x. So this problem is ill-conditioned problem. So easily we can write it as ill-conditioned problem. For vectors, we shall have a norm, that is what is called norm, instead of absolute values. So the condition number of several variables vector can be defined as, we do define like this, and this is what is called gradient. This is called a gradient of a vector field, you know very well, and this is not equal to 0. Anyway, this norm should be free from 0. Then I can define what you call condition number for vectors. Then I can see that what would happen to this system, whether it is ill-conditioned or well-conditioned. Now you see this example, it's very nicely given. If you have x is equal to x1, x2 transpose, fx1 is equal to x1 minus x2, then the gradient of del f is 1 minus 1, and with respect to norm we can write it as this thing. So ultimately it shows that the problem will become an ill-conditioned system. So this is the way that how you can prove that the problem will become an ill-conditioned problem. Now let us look at into the condition number of the matrices. So suppose A is a relative number, x is a vector, say condition number of A can be written as k is equal to the norm of A times of mod x, norm of x upon norm of Ax. So if A is a square matrix, square, non-singular, then we can write it as condition number is nothing but the 2 norm of this A and 2 norm of this A inverse, we could able to get the condition number. So by knowing the condition number, we will be knowing about the ill-conditioned system, well-conditioned system, and also we will see the what you call the stability of the linear systems, how they do behave. So having background of this errors and condition numbers, stability, so we have got enough background. I think we should be able to go ahead in this direction, and I will stop at this, and we will look into the next the course of action in the next lecture. So thank you very much for all of you for patiently listening my lecture, and hope that you have gained a good amount of knowledge, and in the course of time we will have a discussion. Thank you very much.